All right, so I think I recognize everyone's name who I'm looking at here. Just to make sure, this is Math 271, Calc 2. So we're meeting at this time, 6:10 to 9:10, Tuesday through Thursday. So just a little bit about myself. My name is Steve Reese. I've been at ASU. I'm going into my second year, starting this fall as a PhD student in math education. I've been a TA since I came back, and for both semesters this past year, and now including the summer, I've been involved with Calc 2. So I was a TA for the last 2 semesters, and now I'm teaching Calc 2. So I've got quite a bit of experience with this class. By the way, before I go any further, if anybody has any questions about anything, yeah, please go ahead and feel free to stop me. Got one more coming. Also, it is my intention to record all of our class meetings, but I cannot promise that I'm going to remember at the beginning of every class. So feel free to speak up and remind me if I don't do it. But yeah, so something I'm definitely planning to do is to record all of our class sessions and post those to YouTube either night of or next morning. I'm actually not sure quite how long it's going to take me to convert a 3-hour-long video from Zoom. Something I haven't done before. All right. So I'm going to go ahead and share my screen with you. We're just going to go over the syllabus for a little bit here before we actually get into some calculus. So I'm going to go ahead and share my screen. And just want to make sure that you can all see this. Can someone confirm?
Yeah.
Okay, good. And then this is very much an optional request, but I don't know. I feel like these remote classes go better for everyone if cameras and microphones are on. And I say that for a couple of reasons. Number one, I just think it's, I don't know, I think for me anyway, it gets a little lonely just staring at either your first initial or your profile picture or whatever. Also, I am not going to run this class like a traditional lecture. I'm going to be relying on you to give your inputs pretty often. I think that's the only real way to kind of bang your head against the stuff and make sure you're understanding it and make sure you're interacting with it. So this is typically a class you would take in 16 weeks, and now you're going to take it in 6 weeks. Because of that, it's going to move quickly. So a couple of things to say about that. First of all, it is going to move quickly, and there is a lot to cover. But at the same time, there's plenty of time to get your questions answered. So if you, and I don't just mean during office hours or before or after class, just chime in whenever. I'm hopeful that I will see chat if you want to ask your questions in there. But I can't promise that. So by all means, you have my permission at any time to just chime in and just ask a question verbally. See in the chat right now, how many hours a day do you suggest we spend doing problems or studying? Let me hold that question for a little bit. One thing I want to talk about before we actually get into some calculus is what a typical class is going to look like. And before I do that, let's kind of go over some of the broad strokes of the syllabus here. So my office hours, so this class meets at 6:10. I am going to be here I'm gonna open up Zoom every day at 5:30. So if you have questions, yeah, just jump on a little early. It doesn't have to necessarily be 5:30, but I will be here for anybody who needs anything. If that does not work for you, I am very easy to get a hold of by email. So please do that as well. Another avenue that you will all have to to kind of interact with this class is, has anybody used Slack for a class before? Okay, I see one nod. So if you go to your Canvas, and I'm guessing a lot of you already saw this, when you click on Calculus with Analytic Geometry 2, you'll see two options, Canvas and Slack. So I took a class this past semester, or it's actually both of the past 2 semesters, where my professor set this up, and it became a very good place for my classmates and I to bounce ideas off each other, ask questions, offer help, get help, things like that. And I am very much hoping that this gets used for that. I was just about to say Discord. I know, obviously, I mean, I think that's, I use it, a lot of people use it, but really, I am very happy with whatever resource you all land on to get help with this stuff, because I just, I'll shoot you straight. This is going to be a tough class, and you are all going to struggle with things at certain times, but you're not going to all struggle simultaneously. So, here's my first request for you all to reach out to each other and offer help, and to ask for help. And I think one thing I can say about that is that, you know, I know the feeling, and I also know that a lot of you are going to feel at times that, well, I don't want to ask a question because I feel like I'm the only one who doesn't get it, and that's just patently false. So I think everyone has felt like that at one time or another, but yeah, definitely reach out, get help, ask for help, whether it's from each other or whether it's from me, whether it's from, on Discord or Slack. There are also lots of resources online you can consult. But you're going to face some difficulty this summer, and there are resources to remedy those difficulties. So the textbook, we're going to use the Stewart 8th edition of Calculus Early Transcendentals. Is there anybody who doesn't have access to that? I'm going to be using quite a bit of resources from that book. So if you don't have access to that text right now, you're probably going to be okay, but I would try to remedy that pretty quickly. I will say this: you will not need it during class. I'll be providing everything you need during our actual class periods. This class is going to be held entirely remotely, so yeah, we're going to be in this Zoom room for class periods, exams, office hours. I'll be using this for everything. What are we going to be going over? I think, from what I remember, I haven't taken Calc 1 or T8 for Calc 1 in a long time, but Calc 1 is mostly differentiation. Is that the case? Some integration?
Integration is covered like at the very end, but
okay.
It was mostly different.
Okay. So yeah, well, and we're going to be kind of picking up the ball from there. So we're going to be doing a lot of integration, applications of it, things like that to start with, including in just a couple of minutes. But yeah, some of the prerequisite stuff, I'll say, like, we will not be really reviewing a lot of prerequisite material at length during this time. But if you feel like you have some gaps, definitely reach out, and we will, I will set an appointment with you, or I'll work with you. I'll support you in whatever way you need. But if there's something you're missing with the prerequisite material, then I can't promise we can spend a ton of time during class on that, but I will obviously make the time for you. Just that might not be during this block of time. Let's see, what should be expected of you? So be ready to, like I said, be ready to participate often. And this is not going to be the kind of class where basically I talk for a couple hours at a time and you take notes. There isn't a lot you can learn that way. So I I really am going to expect you all to be participating. And that's why that's one reason I'm gonna post all my lectures, so you can, a lot of this stuff, you just kind of have to see it and kind of incrementally solidify things. You know, it's not like it's all gonna click at once for you. That's actually very rare. But yeah, I'm gonna give you plenty of chances to kind of struggle with this and learn these things in real time. Please ask me questions whenever you need. And I know I can't really, it's kind of a hard hurdle to get across, but you know, even when you feel like, oh, everyone else gets this but me, that's just not true. Please, please, please ask me questions. I would encourage you to ask questions for the good of the group. So either ask them verbally or in the chat where everyone can see it. But if you don't feel like you can do that, you can also send me a private message as well. Reviewing your notes daily. So like I said, this class is going to move quickly. So typically this class meets 4 hours a week. We're going to meet 9 hours a week. So it's going to be a little accelerated. So anything you can do to kind of keep pace, you know, whether that's reviewing your notes before class, things like that, reading the text to get a leg up, that would be good. Sometimes it would be, sometimes it's useful to, if when I'm teaching something, maybe that's not the first time you've seen it. Recommended resources. Actually, before I do that, and I think we've all been doing the remote learning thing for the last year or so, and I know it's difficult. There's really no way for me to know if you're looking at your phone or looking at something else on the internet. But just use your best judgment, please. I know life happens, and when the remote thing's a different situation, but try your best to just do that sparingly. Recommended resources. Khan Academy is a great one, not only for kind of tutorial videos, but they have practice exercises you can look at and work through, and they even have work solutions a lot of the time. And Khan Academy is just one of several things where you can find practice problems like that. These next two books, definitely not required. These are kind of just supplemental practice if you want some more problems to look at. I would discourage anybody from buying those, just because there are so many good practice problems that you can work through that you can find online for free. But I have both of these books, and I'll probably be using a lot from them. Tentative schedule. So one thing I kind of glossed over, I most recently updated the syllabus today. This is my first time teaching a summer class, my first time actually being the instructor of record for a class. So I am not, right now, I do not know exactly what I'm going to be teaching on any given day. I've got this week pretty well ironed out, but I don't know, for example, what we're going to be covering on June 17th. It's just, I don't want to throw a moving target out in the future like that. So I have scheduled our exams. They are going to be, if you want to kind of mark those down, they're going to be June 1st and June 16th. Those are going to be the exam 1 and exam 2. Those are the midterms. And the final exam will be on the last day of class, which is June 24th. Those dates are pretty well set in stone. What is not quite set in stone is, the coverage. So right now, I am planning for exam 1 to cover all of chapters 5, 6, and 7. That might not be the case. But I am much more likely to alter what is going to be tested on that day than I am actually to change the dates. Madeline, I'm going to scroll down, and actually I'll just do that now and I'll jump back up. So test dates, it still says tentative just because I I'm just trying to be cautious, but I do not foresee moving those. Something I am planning to do on test dates. So our class periods are 3 hours long. I would like my exams to be about half that long, so about 90 minutes. So my current plan for exam days is to make the first 90 minutes of those exam days to be optional, but basically I'll just be reviewing. I'll be reviewing and kind of your choice what we talk about, what we go over for the first half of those days. I'm saying optional, but I think it's really in your best interest to be there if you possibly can. But then the exams will be the second half of that time. So from 7:40 to 9:10. Let me go ahead and pause for a second. Any questions about anything that I am saying so far? Okay. All right. What are we going over? So, like we said, Calc 1, you know, the lion's share of the work you did was in differentiation. Integration is going to be a big chunk of what we do, especially early on. So integration by substitution, which is probably, I'm guessing review for some of you. We're actually going to get into chapter 5. We're going to do 5.5 and 6.1 today. So a lot of what we're going to be doing, so chapters 5, 6, 7, and 8, these are all applications of integration. Then we're going to get into sequences and series. And then we're going to end with parametric equations and polar coordinates. So these latter two chapters are going to be pretty crucial, especially for those of you who are going to be going on to Calc 3 sometime after this. So note about exams. So in general, I am not going to require people to, you know, have their microphones on or have their cameras on. On exam days, I will be doing that. So my exams are going to be exclusively free response. I'll be proctoring them. And that's why I'm going to insist on microphones and cameras on for those days. If you don't have a webcam or you have a concern about that, please let me know as soon as possible, and I'll try to make arrangements with you. All right, grading, how's this going to work? So 4 main categories. So homework is going to be 20% of the grade. I'm going to be collecting homework on a weekly basis. Those of you who have already started looking at Canvas, you'll see that the first homework assignment is due next Tuesday. And it's going to be due on a weekly basis on Tuesday afternoons. I believe I set the due date at 5 p.m. Quizzes are going to happen on a daily basis. Basically, every class period where we don't have a test, you're going to have a quiz. And I'll go into a little more detail about what that means later, or how those are going to work. Tests are going to be worth 20% each. So those 2 midterm exams on the 1st and the 16th will be worth 20% of your grade apiece, and then the final exam will be 30%. Grade cutoffs, these are minimums. What I mean by that is if you earn a 91%, you're assured an A. If you have an 89%, you're assured a B. You might get an A. It all depends on kind of how things shake out at the very end. But yeah, these grade cutoffs are not going to be any more strict than this. All right, email. So you are welcome to send me emails from whatever address you want. Depending on what you want to talk about, though, I may email you back at your ASU email. There are certain things that we're strongly discouraged from discussing over personal email channels. So just be aware. Be aware of that. If you send me an email from your Gmail, I might not respond to it. And those are just things that are kind of educational FERPA rights kind of things. Quizzes. So the way the quizzes are going to work. Before I get into that, let's talk about homework first. Is everyone here familiar with web work? Okay, so let me go to my web work real quickly. So the address is webwork.asu.edu. These are all the different summer classes. I guess I am the only person who's got a shell set up for Math 271 right now. But if you go here, you will see, if this is not going to look this way to you, I have a lot of different sets here, but only a few of them are open. Right now, if you go to web work, the only problem sets you should be able to see are 5.5 and 6.1, because those are the ones we're going to be talking about today. By the end of the week, 6.2, 6.3, and 6.4 will also open up. So as I said before, homework is going to be due every Tuesday. I would strongly recommend not waiting too long to at least get started on this. Homeworks they're not typically going to be all that short because I'm trying to basically, this class is going to be kind of on a compressed schedule. So in fact, I would recommend that we're going to be, by the end of tonight, we're going to be done with section 5.5 and section 6.1. So I think it would be really good if you at least kind of got a sense for what's being assigned for 5.5 and 6.1. You should be able to do most of it after tonight's lecture. And then I'll be online at 5:30 in case anyone wants to come in and talk about it. Yeah, I'll start holding office hours starting tomorrow. And since I don't really know what web work looks like on your end, is there anybody who's logged into web work and not seen those two problem sets yet? Or does it look the way I expect? Can someone give me a thumbs up or a thumbs down on that before I go too much further?
Yeah, I can see it.
All right, excellent. Thank you. All right. So yeah, homework will be collected every Tuesday. And I'll put in the scores. I'm going to try to be really prompt with my grading because this class does move fast, and I think the feedback is really important for you to make sure that you're. I don't know. I've taken classes before where I have to kind of guess if I'm on the right track, and it's very frustrating. I really don't want to leave anybody in that boat. The way quizzes are going to work. So as you said, the homework is all web work. So you're not going to be turning anything in like a PDF or anything written or anything like that. Quizzes are going to be written. So quizzes are going to take place at the end of each class period. This is a 3-hour class period. Quizzes are not really going to be run the way you might be thinking of, when you hear the word quiz. I am intending for them to be about 30 minutes long, but they're also, you can kind of do them on your own time. So for example, tonight's quiz is going to be due tomorrow at 5 p.m. And because of that, they are open note, open resource. I think the one I scheduled them all that they open up at 8:30. I will be online tonight until 9:10. So if you want to do that quiz while I'm online, that way you can ask me clarifying questions. I will not be helping you with it, but if you have clarifying questions, things like that, you can definitely ask me. But this 3 hours that you're required to be here every night, I'm basically deferring 30 of those minutes to this quiz, and you can choose to stay on after I wrap up class, or you can take that 30 minutes and devote it to the quiz the next day. Alistair asked, will they regularly be due next day? Yes, they're going to be due. Basic quizzes are going to be due Wednesday, Thursday, Friday at 5 p.m. Except for after test days, there are no quizzes on test days. And one thing I want to say about quizzes, I'm not going to be just grading those for correctness. I know there are things out there, not going to mention them, but like there are many things out there that can do integrals for you. So I'm going to be grading you on completeness as much as correctness. So I really want to see that you're communicating how you're getting your answers, how you're coming up with solutions, just as much as what the solutions are themselves. And I think that'll be more clear when in a couple hours you see that first quiz. Technology. So again, use your best judgment regarding cell phones. I know that, life happens when you're taking classes from home. You will commonly hear my kids or my dogs or my family. I understand that life happens and you can't exactly shut everything out, but yeah, just use your best judgment regarding cell phones. Graphing calculators are highly recommended for this course. So I've listed a few models here you can use. Any calculators that do symbolic algebra are forbidden. So TI Inspire, TI 84, I think it's old, but it still works perfectly well. I admit that I don't know a ton about these Casio models, but I know a lot of people who swear by them. But just stay away from the ones that have like the QWERTY keyboards, like the TI 92, or the ones that basically can solve algebraic equations on their own. Exams, kind of talked about that. So yeah, make sure your camera and your microphone are enabled. If you don't have that capability, please let me know as soon as you can, and I will. I'll see what I can do for you. Makeup exams. If there's any possible way that in advance you will not be available for an exam on the day I'm giving it, please let me know in advance, if at all possible. Yeah, I'm not sure how else to stress that. Just let me know whenever you can, and just at the risk of repeating myself again, I'm here to support you in any way possible, like whether that's with a mathematical concept or just kind of logistical stuff or anything. Reach out for anything, and I will do it whatever I can to support you. Important dates. The add and drop deadline is today, which is kind of, it's first day of our class, but second day of the term. So I think this is the last day to drop without that W. 3 exams are in red. I think I've already said a lot about these deadlines here. Madeline asked, will all the exams being free response, or all the exams going to have a similar amount of questions, or will they vary based on subjects covered? Madeline, I cannot guarantee that the number of questions is going to be similar between between the tests, but they're all going to be about 90 minutes long. That's going to be my intent. For example, I think one of the things we're going to talk about later on in the summer is infinite series and infinite sequences. And those questions they're typically shorter than things I can ask you involving integration. Not to say they're easier, they're just kind of a shorter path. So no, I cannot say anything about number of questions, but yeah, the time demand, those are gonna be pretty similar. All right. Extra help. Come to office hours as often as you can, as often as you need to. Make an appointment with me. One nice thing about Slack is that it works really well with mobile devices. So some of you have probably experienced this. It's really hard to get help with math stuff, just emailing back and forth, because a lot of things just don't translate over text, or especially if we're going to be doing a lot of integration. Sometimes a diagram or a graph or a picture is important to that. Slack and Discord make it really easy to send pictures back and forth. So yeah, use Slack if you want to talk to me. Slack to get feedback from your classmates. There's probably already somebody among the group here who's setting up a Discord, so I would encourage them to make that information known so people can use it. There are also tutor centers open for summer hours. I don't think I've posted any links to Canvas yet, but I will do that. But I am hoping that the MC squared will be back to in person. But even if they're not, there's always somebody there on Zoom during the day. Occasional practice documents. If I find things that are useful, I'll put them on Canvas, but they will almost certainly be optional, but never hurts to have more things to practice, especially as exams get closer. Let's see. Just a couple. I mean, the rest of this is pretty boilerplate, but there's just a couple things I want to call attention to. Academic dishonesty. This is a big one for me. Make sure you're representing your work as your own. This is the biggest reason that I am insisting on microphones and cameras on exam days. But even with the quizzes, I'm not going to ask you to work alone on those, because there's no way I could ever enforce that. I know people are going to talk, but please make sure you're representing your work as your own. Inclusivity. Until you ask me otherwise, I'm going to I'm going to use the name and the pronouns that I have for you. If you would like me to use something different, please let me know. Or even if I'm mispronouncing your name, you all have the right to be called what you want to be called. And if I'm doing something wrong, let me know, please. More things by absences. Really, if you can, let me know in advance if you're gonna be absent. I will definitely work with you. It's much easier to work with you before the fact than after the fact. So please let me know as soon as you can. All right, anything else? Does anybody have any questions before we get into this? Okay, so let's actually get into some math here. Before I do, one thing I want to let you know of is that it is my plan to have two things available for you every day on Canvas. In fact, those of you who have gone to Canvas have probably already, well, maybe you haven't opened them and looked at them at length, but you should see PowerPoints for sections 5.5 through 6.4. Actually, you know what? Before we do that, why don't I actually go to my Canvas, see if there's anything else I want to highlight on there. So one thing to look at in here is modules. So class recordings, like I said, I'm going to have a YouTube channel. And once I post the first one there, if you want, you can subscribe to the channel, or you can just go to Canvas. I'll be posting links to the recordings every day. Oh yeah, but right now, under this class notes unmarked, if you want, you can download these 5 PowerPoints and look at them in advance, print them out, do whatever you want, but they're available for you. One thing that I intend to do after every class period is in this class notes marked, which is probably, no, it's not even the thing you can see right now. So I'll publish it, but right now it's empty. Basically, I'm going to annotate on my PowerPoints, and I'll be posting those after the fact. But just like the recording, I might forget to do it. So please, if you don't see those, by the next afternoon, definitely, yeah, don't be shy about reminding me to do it, because something I definitely think is important for you to have access to.
Can you start recording before we hop into the slides?
I think I already am.
Okay. Yeah, sorry, I didn't see the little
No,
button.
that's okay.
Thank you.
But yeah, if I can almost promise that I'll forget to start that recording someday. So yeah, definitely remind me. All right, so this is the only real foray we're going to have into chapter 5, which is the substitution rule. Have people done integration by substitution before? Is that something that we hit in Calc 1? Okay. If not, then let's get into it now. So let's go back to Calc 1 time here. And I'll give you a few minutes here. Find the derivative of this function. So take a couple minutes on that, and then I'll ask for some feedback from some of you. All right, so how do we handle a function like this? How do we find the derivative?
The chain rule.
Chain rule. So what about this thing suggests that the chain rule is important? So you're absolutely right. The chain rule is crucial to find this derivative. But what about this function tells us that we should use the chain rule?
It's a polynomial raised to an exponent.
Yeah, so we have, so you said polynomial raised to an exponent. What if this was something else? Like, does it have to be a polynomial? Could I use the chain rule if this is like a trig expression in here?
Yes.
Yeah, absolutely. So really we have two obvious options here. I could either use the chain rule on this, or I could expand this to the 7th power and then take a derivative directly, which something I don't really want to do. So yes, chain rule, but how do I make that work? What's this derivative going to look like?
Set u equal to 3x squared minus 5.
Okay.
So it's u to the 7.
All right, so now we're transforming this. So then if we want to write this in terms of u, f of u equals u to the 7th. Okay. It's a good first move. Now what?
And then take the derivative of u times the derivative of 3x squared minus 5.
Okay. So basically we're just doing chain rule here. So I am going to take the derivative of u to the 7th with respect to u, which I'm going to write a little differently. So 7 times something to the 6th. And then the next thing I want is the derivative of 3x squared minus 5. Here, did I give myself enough room? 3x squared minus 5. So now we have to so we kind of did the derivative of that outer function. What's the derivative of 3x squared minus 5?
6x.
All right, so last move here, simplify, 42x. 3x squared minus 5 to the 6th power. Any questions there? All right. So now let's go the opposite way. Now I want to find the antiderivative of this thing. And I'm going to rely on something that Alistair gave us, which was this expression for u. So u equals 3x squared minus 5. So I want to find the antiderivative. So basically what I want to do is this. I want this here, the integral of f prime of x dx. And based on what we just did, hopefully it's somewhat clear what we need to wind up with. So what we're going to be kind of doing here, we want this u here to kind of give us a map to transform this integral in terms of u instead of in terms of x. So I can very easily, if we agree with what Alistair gave us for that last example, we can very easily drop in this 3x squared minus 5 in for x. So this integral is going to become the integral of u to the 6th times 42x dx. Now, can I just integrate this in the form that it's in right now? Am I allowed to handle this integral the way it's written? So the answer is no. And the reason for that is because basically the only thing we have in our toolkit right now, when we're taking derivatives or when we're finding integrals, we're kind of stuck to one variable. So the fact that I have u to the sixth here, but really the rest of this integral is written in terms of x, I'm stuck. So I have to express the rest of this stuff, the stuff that's in terms of x, I have to express that in terms of u as well. So we look at our integrand here, we have f prime of x, which isn't going to be in terms of x, but we also have this differential term, this dx. So if we want to integrate this with respect to u, we need to somehow get a differential in terms of u. We need to get a du involved. So one way to do that is to take this expression for u, and we're going to build this up slowly. I want to find du dx. So what is du dx going to be equal to based on this u? First of all, what does du dx mean?
The derivative of u with respect to x.
Right, it's the derivative of u with respect to x. So what is the derivative of u with respect to x in this case? Okay, Jacob says 6x in chat. So I got du dx equals 6x. And then I'll take that one step further and I'll get du equals 6x dx. So that's going to help me here to continue transforming this integral. So the u to the 6 is already good, but now I want to get rid, or not get rid of, but I want to transform this 42x dx. I want to substitute this in terms of something in terms of u. So how can I do that? Based on what I have for du equals 6x dx, how could I re-express this 42x dx? Okay, I got 7 du. And I'll just take this one step further. If du is equal to 6x dx, then I'll just multiply 7 by both sides. I get 7 du equals 42x dx. And I'll rearrange this a little bit. 7u to the 6th du. So now through substitution, I have a much friendlier looking integral than the one I began with. So now, what is the integral of 7u to the 6th with respect to u?
Would it be u to the 7th?
Yep, just u to the 7th. And I'm going to be really nitpicky since this is our first integral of the semester. What am I missing?
Constant of integration.
Yeah. All right. So one last thing to do here is, since we started this whole process to find some antiderivative of a function of x. I want to go back to that. So we know that u is equal to some expression in x. So we're just going to make that substitution at the end here. 3x squared minus 5 to the 7th plus c. And hopefully it's not a surprise that that is where we wound up. Any questions on those first couple examples? All right. So let's do another one here. So like I alluded to before, you do not need, good. We do not need polynomials. We can do this with any kind of expression here. Let's deal with this one. Very difficult integral to handle without substitution. So if you want to use substitution, really the first step in the process is to kind of name your candidate for what that u is going to be. Basically, how am I going to start translating this this integrand into something a little more digestible? So Alistair, you chose what was it, 3x squared minus 5 for your u. How did you make that choice?
It just seemed right. Like that seemed like the most complicated part of the equation. So
Okay.
yeah.
And that's fine. I mean,
For
really, a
the-
lot of this is it's gonna eventually, well, hopefully anyway, it's eventually gonna kind of jump out at you. Does anybody else have a candidate for what we could use for u in this example? Okay, Madeline says x to the 4th plus 2. So let's give that a try. So like I alluded to, so we want to translate x to u. Basically, we have an integrand written in x, want to translate that to u. But we also have to do the same thing with dx. So next logical step from here is that since u is equal to x to the 4th plus 2, we need to figure out what du is equal to. So du dx is going to be equal to 4x cubed, which means that du is going to be equal to 4x cubed dx. So these are our two kind of basic building blocks now. I want to transform this whole integral, and really the only substitutions I'm allowed to make are these ones. I have an expression for u and an expression for du. So based on that, can I start swapping things out of this integral? What's one change I can make?
Just in terms of rewriting it, you can have x cubed cos u dx.
Okay, so yeah, that's one thing we need to do is to start translating this in oh, wrong. Well, how do I erase? There you go. Okay. So we've made a dent in this, but now we got to keep on translating this to u. So we've got x cubed dx. Can I express that in terms of u somehow?
Could you do 1/4 du times
Yep.
the cosine u dx?
Yeah,
Or
and that's
cosine u.
right. And that's one thing I want to point out here. So, so here we had du equals 4x cubed dx. One thing you can do here, if you notice it, or really you can do it at any time, but I know that I eventually want to get this, that x cubed dx is what I need to is what I need to translate. So I can kind of work ahead here and solve for x cubed dx, and that gives me 1/4 du equals x cubed dx. So that allows me to rewrite this entire integral as 1/4 cosine u du. Any questions about how we made that substitution, that translation from x to u? All right, so now that we've done that, the substitution's been done. So now we can do the integration. So what is the antiderivative of cosine u du?
Negative sine u to the second. Oh,
Negative,
or the,
sorry,
actually,
negative.
yeah, just negative sine u.
Okay. How do we feel about that?
Oh, wait, isn't derivative sine cosine just cosine?
Yeah, so this is actually just positive sign. And that's kind of that's something that, I mean, I've been doing this for 20 years and I still have to think about that, especially when you're doing integration. So one thing that I typically do here is, if I'm going to go the derivative way or the integral way, what's the derivative of sine of x?
Negative cosine x.
It's just cosine x. If I'm just doing derivatives now. I don't know, this is just a kind of a organizational tool that I use when I get lost on these sign flip things. What's the derivative of cosine x?
Negative sine x.
Negative sine x. And then I already know that the derivative of sine is cosine, so those will be negative cosine x. And then it just works back up to the top. And really the integral, really the flow is just opposite. So I don't know, maybe this is probably true for some of you, at least, that probably have a much better idea what the differentiation rules are for these trig functions. So if you need to, just write them out so you can, if you help you take them backwards. All right, so what's my last move here?
Plug back in for you.
Yep. So 1/4 sine of, what did we say? X to the 4th plus 2. Let's see. All right, any questions there? All right. So I'm going to give you the substitution rule, the way the textbook kind of lines it out. And I'll admit, this is not something I use a great deal. I think it makes more sense to just kind of go through the process of substituting. But if this is useful for you, have at it. So we want our u to be some differentiable function. So the ones we've used so far, they've been polynomials in both cases, which are always differentiable. We want f to be continuous on that same interval, which we haven't really looked for, but so far we've been using functions that are continuous everywhere. So long as I meet those two conditions, then I have this. I can basically substitute the integral on the left for this much simpler integral on the right. It probably was not obvious that this is something we were doing. But this thing on the left here, what does this look like to you? Where have you seen this before?
Is that the product rule?
Not the product rule. It's another very important rule for, what was that?
I was going to say the chain rule about that.
Yeah, this is the chain rule. Basically what the chain rule looks like is this. If you take the derivative of some composite function, then you get the derivative of the outside function with the inside function left intact times the derivative of the inside function. So yeah, there's not a coincidence though that those things look very similar. The substitution rule, basically you're kind of reworking the chain rule. You're going the opposite direction. Any questions there? All right, let's do a couple more examples. All right, so the integral of square root of 2x plus 1. What's the first thing we should be trying to do?
Define u.
Okay, define u. Well, what's a good candidate for u?
2x plus 1.
X plus 1. All right, so this is the third one of these now. How are we choosing this expression for u? What are we looking at? And this might actually make sense with this last slide here. Even though this is all in generalities, basically you're choosing this u here. What does u equal to if you kind of correspond it to the left-hand side here?
G of x.
G of x. And it's not a coincidence, that's usually what you're going to do. Because really what we have here is a composite function. So we have some inside function, which we're calling 2x plus 1. What's the outside function in this case then?
Would it just be g of x to the 1/2?
Yeah, I mean, so yeah, it's just x to the 1/2 or square root of x. Because really what I'm doing is this, I am composing f with g. So if f is a function that takes the square root of whatever its input is, then yeah, I'm just f of g of x is going to be the square root of 2x plus 1. All right, so we got u equals 2x plus 1 that we're going to try. Now that I have this, what else do I need to do?
Get the derivative of u.
Okay. So du dx equals 2, which means du equals 2dx. All right. Now, do we make a good choice for u and du? Can I actually start translating this integral with it?
Yeah, so with this one, you would have, if I'm remembering how to integrate properly, you would have u to the 1/2 plus 1 divided by, so it would be like,
Oh, so I see where you're going at. Let's not integrate yet. Let's just make sure
okay,
let's actually just set up the integral in u first. But yeah, here's a good place to start. U to the 1/2 dx. So we're not quite there yet because I have to get the differential term for u in there. So what else now?
Then it would be 1/2 and then the integral of the square root of u du.
Good. All right. And then from there, yes, we can integrate 1/2. What's the integral of u to the 1/2?
Two u to the 3/2/3.
I think that's what you said.
Yes.
Okay, good. All right. All right, is that it?
Let's see.
Let's see. Oh yeah. All right. So simplifying, we get 1/3. And then now we're at a good place to undo that substitution. And there you go. All right, any questions here? Okay. Let's see what's left. All right. Let's go a little quicker this time. What's u?
1 minus 8x squared.
What's du?
So negative 16x.
And dx.
Yep. Are you ready for me to just ask you what this full integral is going to be? Or should we still break it down in steps? Got one vote for steps, so come and give me the first move here for translating this integral.
You substitute u in.
So I'm going to have x over square root of u dx.
And then I know you need to get u inside or du,
Mhm.
but I don't really understand how to.
So let me ask it this way. Basically, anything that has an X in it is, forbidden. Basically, we want to substitute fully. So we already got this 1/8x squared. That's been translated in terms of u. But now we have to get rid of x dx. Or not, I guess get rid of it is the wrong language. We have to substitute this in terms of u. So really our only two weapons here are, we have an expression for u and we have an expression for du. The expression for u has, you have two terms added together and you have x squared. So I don't think that is going to help with this. But the du here, that has one term. The x is linear, and it also has that dx there. So I'm sorry, go ahead.
Oh, I was gonna say, so do you solve for x dx? And
Yeah,
then-
that's very good move. So what's x dx equal to?
du negative 1/16.
And I'm glad that question came up because, my general advice for, setting up an integral by substitution is, just keep consulting these two things here. Because basically these are the only two avenues you have for making substitutions on your integral. And really we haven't done it yet, but if you choose something for u that won't work, you won't be able to finish the substitution, and you'll know that you need to go back and try something else. Yeah, maybe I need to do that on purpose on one of these to kind of give you something to compare and contrast. So now that I have this, which really is just a re-expression of this du expression, I can do this. I have the integral of negative 1/16. Are you okay if I do this? U to the negative 1/2 du.
I guess what's throwing me on this a little bit is that in the previous example, du is simply equal to 2 dx.
Mhm.
And here we have du equals negative 16x dx. So that x just throws me off a little bit. Like, do we ignore that? Like it makes
No,
sense that. Yeah, sorry, go ahead.
I'm sorry. Go ahead and finish your question, Alistair.
No, that's that was basically it.
Yeah. So the short answer is no. We can't ignore it. For example, if you just had dx over radical u, then this substitution wouldn't work. So yeah, I mean, and really this x being here, this is all a function of what u looks like here. Let's say I had, I don't want to call it u to confuse the matter, but let's say I had like z is equal to 10 plus x to the 9th. Then dz would be equal to 9x to the 8th dx. So if I was dealing with an integration by substitution like this, then I would really need to have, some multiple of x to the 8th multiplied by my dx to finish that substitution. So yeah, I mean, in the last one, yeah, it was basically what you had was a constant rate of change. That du dx was just equal to 2. But really, you're not going to have that most of the time. I think for the very first example we did, if memory serves, that was a quadratic, so the derivative ended up being linear.
Right. Yeah, I know. Like, we're not finished solving this problem, so maybe we'll get there. So why does like negative 1/16 u to the -1/2, or like,
Oh, so this is, so the u to the -1/2, that's just an exponent rule.
no, I understand that, but like,
Okay.
shit, let me try. Like, for the last problem, we multiplied, to get dx to du, we multiplied the entire integral by 1/2, correct?
Oh, that's a good point. Okay, so
And now we're doing the same here to get rid of the 16, the -16, but I'm wondering what's going on, what happens with that x?
the x basically gets absorbed into this du. And that's really just the nature of our expression for u. And one step I kind of omitted from this is this. Du dx is equal to -16x. So when I'm translating or trying to substitute to get that du differential term, basically I'm going to do that at the cost of some x term, some x to the power of 1 term.
Okay, sorry if that like derailed things, but
No, you're not derailing things at all. It's good to be able to understand these, why that's happening. One thing that I think kind of got glossed over is, hopefully it's okay with people that, there is no mathematical difference between me leaving this -1/16 inside the integral or removing it. So if I have a multiplied constant like that, that's perfectly fine to do. Now, what is the integral of u to the -1/2?
Two times u to the 1/2.
2 times u to the 1/2. So this all comes out to be -1/8 square root of, let's just finish it, 1 minus 8x squared. Let's see. How are we doing there?
makes sense.
All right, and this one, let's skip over that one. Yeah, this is a good one to do. So let's do this. We've been going at this for about almost an hour and a half. Let's do this one, then we'll take a little bit of a break. And by this point, I don't think we're really, I'm not saying really anybody has this impulse to do this, but I do want to show you an example of what it looks like when you make a bad first move here. So let's say that u is equal to x squared. That would make du dx equal to 2x. And then du is equal to 2x dx. So now what does that look like if I start trying to transform this integral? That's going to give me the square root of 1 plus u times this x to the 5th, that'll become like u to the 5/2. And then I'll have a dx left over. But now based on this, like, I have du dx equals 2x. Let's go one step further here. If I wanted to solve this dx, I'd have dx equals du over 2x. I don't really have a good avenue for translating this dx to something in terms of u. So that's one caution I'll give you when you start working on the homework or looking at the quiz at the end of the night is, and it really all stems from you. I mean, your du is totally beholden to whatever you chose for you. So really that all comes down to that one choice, what you made for you. So if you make that choice and you can't finish the substitution, it could mean there's something it could be there's a mistake you're making. Or it could just mean that your expression for u is kind of a dead end. So keep an eye out for those things. So u equals x squared doesn't really get us to where we want to go. What's a good expression to use instead for u?
X to the fifth, maybe?
What was that? X to the fifth? I think I heard x to the fifth. All right, if u is equal to x to the fifth, then du dx would be 5x to the fourth. And du would be equal to 5x to the fourth dx. All right, so let's start substituting. So I think this is going to become 1 plus x squared times u dx. And then what can we do? Can I do something with this x squared into the radical? Or to translate that dx?
So to get du, would you just multiply by 1/5?
To get du multiplied by a fifth? 50 u equals x to the fourth dx. All right. But now I think we have a different problem. Do I have an x to the fourth in my integrand that I can take advantage of?
We do not.
No. So I think this is one of those times where I do not think u equals x to the fifth is going to get us there. So we tried x squared. We tried x to the fifth.
What, like, when you say u equals x squared, are you saying that, like, because my initial instinct was to make it u equal to the entire expression underneath the radicand.
Yeah.
So, yeah.
So yeah, let's give that a try. So let's go from there. So if u equals that, what does du equal?
2x.
2x dx. So now I can start this substitution. So I'm going to have u to the 1/2. And I'll just leave the rest x to the fifth dx. So this one's kind of tricky. So I'll tell you right now, this u will work, but I don't think it's quite as straightforward as some of the other ones. So we transformed the radical there, but now we have this x to the fifth dx. we know that to substitute our dx, basically we have to substitute x dx in order to get du to show up in this integral. But this x to the fifth is kind of making this complicated.
I might be forgetting integration rules, but could you split this up into two separate integrals where it's integral of u to the 1/2 plus the integral of x to the 5th?
That only works if you have things like, if, for example, I had this. So those integrands would have to be added.
Okay.
You just split them up. So yeah, in this case, that would not work because they're multiplied together. So let's look at the basically the expressions we have: the expression for u and the expression for du. One thing I'll do here, we know we need a single x. So I'm going to do this: u to the 1/2 times x to the 4th times x dx. Does that make it any more clear that I can do a little bit of chipping away to introduce more u's into this?
Can we substitute x for something else?
X for something else?
I
You
don't know. Oh,
I don't think I followed the question. I'm sorry.
I'm sorry. It's just some weird idea.
So let's drill down a little more specifically. I know du equals 2x dx. If I look at where my integrand is now, and really the thing that's important to zero in on is the powers on x. So I have x to the first dx. I have x to the first dx here. We've kind of seen with these previous examples that, you know, if I'm off by a multiple of 100 or 1,000, whatever, you know, I can adjust for those multiples. It's really the powers on x that I can't negotiate.
So would we just factor out like x to the 4th or?
Yeah, I've kind of done that. So I've rewritten x to the 5th as x to the 4th times x.
So would the end thing we want be 5/2 du?
5/2 du. I can't do that because really let's kind of follow that out here. If I did 5/2 du, that's just going to give me 5x dx. So really, then that's kind of what I was saying, where you can you have some negotiability on the constant, but the power of x here I can't really escape. So can I do something to substitute out this x dx based on, ooh, no. Based on these expressions up here, is there anything I can do to swap out this x dx in terms of something, in terms of u?
I mean, x dx would just equal a du over 2.
Yeah. And yeah, that's something we can do. So yeah, 1/2 du is equal to x dx. So let's go from there. And then the last part of this is x to the fourth. So based on what I have up here in terms of u and du, is there any way for me to write x to the fourth in terms of u? And really, I can kind of isolate it to u because this is just x to the fourth. I've already substituted out, I've already transformed the differential term. So really, I want to get this x to the fourth in terms of u. And the only way I can possibly do that is through this equation, u equals 1 plus x squared.
So would it be like 2u plus 2? Or minus
2u,
2?
2u minus 2, how'd you get that?
Because if you wait, never mind, never mind.
Here's what I think you did. It seems to me like you moved the 1 over, and then you multiply both sides by 2. So I think moving over that the 1 was good. But is there something else I can do? Because really, I want x to the fourth here, right?
Square both sides.
So
Yeah, Mona Lisa says to square both sides. Which, that does get me where I want to go. U to the 1, u minus 1 to the fourth equals x to the fourth. So that's it. That's the whole thing. So then from there, I'm going to have, I know x to the fourth equals u minus 1 to the fourth times u to the 1/2 times 1/2 du. Nope, I messed up. I mean, this still works, but this is simply squared. I'm going to pause here because I think that's, or I know that was by far the trickiest part of this example. Any questions about how we got to where we are right now? Okay, I'm going to fast forward just a bit. So expanding this binomial here gives you u squared minus 2u plus 1. All right. Now let's finish this thing. What's the integral of u to the 5/2?
to u to the 7/2 over 7.
Yep. And next, this one's going to be 4u to the 3/2 over, no, 5/2 over 5 plus 2/3 u to the 3/2 plus c. And I'm kind of accelerating a little bit. If anybody sees any errors, please let me know. And then our last move here is to resubstitute 1 plus x squared, 7/2. I believe that is correct, but if anybody sees any problems, please speak up.
On an exam, could we just leave it in the U form? Like if we do everything right up until that like last bit to save time, like could we just do like 1 over or just leave it like U 7/2/7 minus 2U?
Depends on what I'm asking for. If I wanted to re-express my final answer in terms of x, then yeah, you would get almost all the credit for this. But yeah, just totally depends on what I ask you for.
Okay, thank you.
Any questions on this one? All right, I have 748. Let's take until 758, and then we'll get going on with our next section. Sound good? All right, I'll see y'all then.
Thank you, Professor.
Thank you.
Professor, I was thinking about that method. It'd be how to get to x raised to 4. So what I sort of like did was like I took u squared, and then I squared the, and then I got back to u minus 1 the whole square.
Let me pull it up again, make sure I'm following you right. So tell me again what you did.
So I took like u equals x, that x squared plus 1, and then I squared u to get x raised to 4.
Okay.
And then I just messed did the whole step to get u minus 1 the whole square. Like I
Yeah.
could have just substituted that.
Right. And I think, yeah, if you take it at that first step where u equals 1 plus x squared, if you square both sides there, then you end up getting on the right hand side 1 plus 2x squared plus x to the 4th.
Oh yeah,
Which
yeah.
I I believe will still work, but that 2x squared is going to be something you have to deal with.
Yeah.
All right, I have 7:58. Let's go ahead and get back into it. So one thing I wanted to talk about, kind of as a logical follow-up to integration by substitution is doing a definite integral. So we'll do a couple of these, then we'll start talking about area. So the bulk of this is not going to change much. All right, so what's a good expression to use for u with this integrand?
3x plus 6.
3x plus 6 is good, which means du is equal to what?
3 dx.
3 dx. All right, so from there we can start transforming, and for right now I'm going to put x equals 10 and x equals 1 for reasons that I hope will become clear in a bit. I know that I have u to the 1/2 dx. So what should I substitute in for dx?
One-third du.
1/3 du. Just to make that really clear, dx equals 1/3 du. All right. So now that we're doing a definite integral, so we're going to have limits of integration. Remember, these limits of integration that I first gave you, these are both going to be in terms of x. So something else we also want to do is to translate those limits. So instead of x equals 1 and x equals 10, I want to have corresponding values for u. So if x equals 1, what does that mean that u equals?
Would it be 9?
It would be 9. How'd you get that, Jacob?
I plugged in 1 to u,
Yep,
or for
that's exactly,
x.
yep, that's exactly it. So remember, this whole process comes from, my expressions for u and du. This is already a recipe for how to translate x values to u values. So I got u equals 9. And corresponding to that, I have, if x equals 10, what is u equal to? Got 36. And now from here, I'm going to drop off those u equals 9 to 36 of 1/3 times u to the 1/2 du. And that integrates to 1/3 times u to the 3/2 over 3/2. Evaluated from 9 to 36. All right, I believe that's all correct. And this is where it gets a little bit different. So any questions about where we are so far? Does it all look correct? Do you understand how this happened?
Real quick, why does it turn to 3/2?
To 3/2. So this is basically power rule of integration. So integrating u to the 1/2 basically add 1 to 1/2.
Oh, okay, I see.
Yep. And then from here, it's just a matter of evaluating 2/9 times 36 to the 3/2 minus 2/9 times 9 to the 3/2. So everything we did before the break was indefinite integration. And when we were done with those, our final answer was a function or a family of functions that were all kind of united by, an arbitrary constant of integration. What's our final answer going to look like for a definite integral? What am I going to be left with?
Just a number.
It's just going to be a number, right? All right, so if someone wants to double check me here, I believe 36 to 3/2 is going to be 216. And 9 to the 3/2 is going to be 27. And this part I'm even less sure of it. I think this comes out to be 48 minus 6, which is equal to 42. So one thing to note here, our final answer is just a number. Is there something you might have expected we needed to do here, or something that we did on all of our other examples that we didn't do this time?
The plus C.
Well, plus C, yeah, so yeah, that was not what I was looking for, but yeah, so when you're doing definite integration, you're not going to get that arbitrary constant. We also didn't have to translate this back to X.
Oh, but you what about you? Wouldn't you have to put back U or something?
In this case, no, we don't. So for a definite integral, our final answer is just going to be a constant. It's going to be a number. And the whole point of substitution is I'm taking this integral, which is pretty complicated, and I'm going to trade it for another integral that's simpler. And the fact that not only did I substitute the integrand and the differential term, I also substituted my limits. So basically, I have traded out that integral for a mathematically equivalent one. So this number 42, that 42 is not a function of X or U. Both of those integrals would have given me the same thing. So when you're doing a definite integral, there's no need to do that reverse substitution. Any questions here? Right. Substitution rule. Basically, the only addition I made for this slide here is putting limits of integration on it. But again, you're still just kind of you're unveiling, you're undoing the chain rule. And just to something kind of impress on you, with all the other examples you did, you were translating your given variable to some other variable. You also have to translate your differential term with respect to that new variable. But now this last thing we're having to do is you have to swap out the limits as well. So, but really, integration by substitution has a lot of commonalities, whether you're doing a definite integral or an indefinite one. So I'm usually going to start with U. What's a good expression for U for this integral here?
3 minus 5x.
3 minus 5x. And it means that du is going to be equal to -5 dx. Now, before we go too much further, let's use this expression for u to translate my limits now. So I have x equals 1 and x equals 2. If x equals 1, what's a good corresponding value for u?
-2.
-2. So yeah, 3 minus 5 is -2. And then similarly for x equals 2, I get 3 minus 5 times 2 is going to give me -7. So now I can put these things in for my integral. -7 upper limit, -2 lower limit. Let's do this a piece at a time. Dx over u squared. What can I do about that dx?
Substitute it for -1/5 du.
Yep, there you go. So now this will be the integral from -2 to -7 of -1/5 u to the -2 du. All right, what's this integral going to be? What's the integral of -1/5 u to the -2?
U over 5.
Yep, it should be, yep, 1/5 u, evaluated from -2 to -7. All right, someone finish this up for me.
-7 over 5 u plus 2 over 5 u.
Close. Remember, you're plugging these numbers in for you.
Right, so a -7 over 5 plus 2 over 5.
Oh, you know what? I made a mistake here.
A -1.
This is so this u actually should be in the denominator. It's not u over 5, it's 1 over 5 u. Maybe I should put an intermediate step in here to make that more clear. This is going to be 1 over 5 u to the -1. Raise the power by 1, then divide by -1. Right. Sorry if that was confusing, but hopefully this is more clear now. So then from here, I should get -1 over 35 plus 1 over 10. I believe greatest or least common denominator is 70. Any questions here? All right, I think I want to move forward a little bit to this one here. So now we're going to use, and this is probably something you did near the end of Calc 1, using integrals to find area. So got a screen capture here of a graphing calculator of this function, y equals x times e to the 4x squared plus 3, bounded by x equals 0 and x equals 1. And we want to find this shaded area. So in order to find an area, how do we do that using calculus?
You can use Riemann sums for an approximate area or integration.
Yeah, so we want to do this as exactly as possible. So what's the integral going to look like to find this area?
Would it be from 0 to 1?
0 to 1. Yep. And what am I integrating?
Would it be x times e to the 4x squared plus 3?
Yep. So yeah, to find the area underneath the curve like this, really what we're doing is integrating the function itself over the integral that we're interested in. So hopefully that's familiar from Calc 1. And if it's not, that's fine. It just means we gotta go a little slower than I had planned on, but that's fine. So now basically, yeah, we haven't really been dealing with areas explicitly, but really we're just finding this definite integral as we just did a couple of times. So now from here, what should I do to continue?
Find our u.
Okay, what's u going to be in this case?
4x squared plus 3.
4x squared plus 3, which means du is going to be equal to what?
8x dx.
8x dx. Good. Let's actually keep on translating. So we are limits of integration of x equals 0 and x equals 1. So what does that mean for the corresponding values of u?
For 0, it would be 3.
Mm-hmm.
And then 1, it would be 7.
Yep. So now we can start translating this integral. So integrating from 3 to 7. Got e to the u times x dx. And then how am I going to handle the x dx part of this?
Put in 1/8 du.
Right. So 1/8, I'm going to put it on the outside. Times the integral from e to the 7th, e to the u du. All right, what is the integral of e to the u with respect to u?
Just e to the u.
What's that, Mona Lisa?
Sorry, is it just e to the u?
It's just e to the u. Yep. So yeah, it's that special function that's its derivative and its integral are, yeah, they're equal to itself. So then from here, now you're just evaluating. So I get 1/8 times e to the not e to the 7th. E to the 7th minus 1/8 e to the 3rd. If you want to punch that into a calculator and get an approximation, you can, but that is that area. Any questions on that one? Okay, so that is actually all I have for 5-5. But I want to, the reason I did that example there is because I wanted to use that as a transition into area between curves. So I'm going to go ahead and share a new one now. Can you all still see my screen?
No.
No? Okay. That's not right. All right, so we're not going to go through this at length here. Just kind of want to get you thinking about the right things. So I have this weird shape here. I'll give you the pertinent dimensions, but how would we find the area of this thing?
You find the area of the rectangle and then subtract out the area of the triangle and the half circle.
Right. So yeah, I mean, we don't have some canned geometric relationship for whatever this shape is. So because of that, you're kind of stuck with, you know, treating this in terms of a composite of more basic things. So our last example we just looked at, we just did the area underneath a curve. Now what we're going to be looking at is the area between curves. So we want to find this area here, bounded by these curves. So our first one, I will go ahead and roughly sketch out what this looks like. X equals 0, it's going to be the y-axis, x equals 1. One, two. So I know that my line y equals x is going to look something like this. Hopefully it doesn't bother you that I'm not 1-to-1 scale. So there's my line, and my curve is going to be going to cross the y-axis at 1. E is about a little more than 2, so it's going to look something like that. So really, this is the curve or the area I'm looking at here. So I'm not going all the way down to the x-axis. I'm just basically below that curve and above that line. I'm trying to find that area. And just because I'm curious, I want to see if this is something you've done before in Calc 1. How would we find this area? I mean, just a few minutes ago, we found the area under a single curve. So can we adapt that to find the area between these two curves?
I mean, I don't mean to, I'm not trying to hate on your drawing ability here. Are those meant to be curves or straight lines?
The one on the bottom is meant to be a line. The one on the top is meant to be a curve.
Thank you.
I know my drawings are bad.
Would you do the integral of the top one minus the integral of the bottom one?
Okay, so let's do this. Let's find the area. That's going to be equal to area 1 minus area 2. Now let's set up the integral for each one. How would I find that first area, basically the upper area? What's that integral going to look like?
Would it be from 0 to 1? Then EX dx?
Very good. And then what's that other one going to be? The integral from what to what of?
It'd be 0 to 1 x dx.
There you go. So yeah, this would absolutely give it that area. Just basically what you're doing here is kind of the same thing we did in that weird geometric shape. I'm going to find this area under e to the x dx. I'm going to find the area under x, and then I'm going to take their difference. So I think we just said the integral of e to the x is e to the x. And what is the integral of x?
X to the 2 over 2.
Yep. So x squared over 2. Also evaluated from 0 to 1. And then it's just a matter of basically evaluating these. So they got e to the 1 minus e to the 0 minus 1 over 2 minus 0 over 2. So e minus 1 minus 1/2, and that's it. So it looks like we did 2 integrals here, right? Any questions on this first one here? All right, let's take it a little further. So this is the example we just did. This is obviously better than my drawing, but we just used 2 integrals to find this area, right? So just a kind of refresher to basically build up an integral. You know, really what we're doing, when we're integrating, all you're doing is you're finding the area of a much more basic shape and doing it an infinite number of times. So really, all an integral is doing is this. So I'm just going to take a little thin slice here, and I'll call that dx. That basically, that width right there is dx. So what I want to do with that dx is I'm going to pretend these sides are straight. That's going to be too hard to do. Let's make that a little less off. Not bad. So I'm going to take that little interval there, make the top and bottom horizontal. And basically what I'm doing here is making a rectangle. I'm going to find the area of this rectangle. And basically this rectangle that I've drawn there, that's just one interval. There are 2 things I'm going to do here, and then hopefully a lot of this sounds familiar from your Calc 1 days. I'm going to make enough rectangles to cover the entire interval from x equals 0 to x equals 1. And then I'm going to make those rectangles so narrow that they effectively have a width of 0. But before we get there, we can just kind of talk about what I'm doing here. So basically, I'm finding the area of these rectangles here. So we all know how to find the area of a rectangle. How would I find the area of this rectangle here? How do you find the area of any rectangle?
The base times height.
Base times height, right? All right. What's the base width of this rectangle?
Dx.
Dx. What is the height of this rectangle?
Y.
Okay, I got one vote for Y. Well, I mean, I got two different Ys here, so which one do I want to use?
The subtraction, like you
Okay, so what are you subtracting?
the e raised to x minus x.
There you go. So, and like I said, this is just one rectangle. I'm going to do this for all the little subintervals of my interval 0, 1. So basically what I'm doing is this. I am adding up, starting with n equals 1, or I want to say I equals 1, going up to n of all these little areas. And you know what, let's bring some generality to this. I'm going to call this upper function f of x, and I'm going to call this lower function g of x. So really what I'm adding here is bunch of areas of rectangles. So that height is going to be whatever the difference is between these two heights is, multiplying that by dx. And like I said at the outset here, I really want to know what's going to happen after I make the intervals so small that they essentially have no thickness and there's infinitely many of them. And from that, we're going to get this integral, the integral from a to b of f of x minus g of x dx. So how many integrals am I looking at here? So hopefully you're all seeing that this is really just, I can find this area between curves with just one integral. Even though in that last example, we took basically those two different areas and found their difference. So really, if you understand what the upper curve and the lower curve are, you can find the difference of those curves and then take that integral. Because really a Riemann integral, which is, that's the integral that you've been doing since Calc 1. All it's doing to find the area underneath the curve or between two curves, it's just finding the area of infinitely many rectangles and adding those together. And really, if I want to find the area of a rectangle, I can just find the difference between the base, the bottom, and the top. I don't need to deal with that in terms of two separate rectangles. So let's do another one here. Now I want to find the area of the region enclosed by these two curves. And in this case, I am not giving you an interval. I'm not giving you a beginning x value and an ending x value. We're just doing region enclosed. So in order to go any further, I have to figure out where my interval is. So how would I find my beginning and my ending x value?
Would you set them equal to each other?
Yep, I want to find out where those x values are, where this region ends. So I'm going to have 2 radical x equals x squared over 4 and start solving.
But how do we know like which one to subtract? Like
So we'll get to that. But first we need to figure out kind of what our intervals we're looking at. But that's a very, very good question. That is something we'll have to do. So how would I solve this thing from here?
You could divide each side by 2.
Divide each side by 2 gives me radical x equals x squared over 8.
And then square both sides.
Squaring both sides, that's going to give me x equals x to the 4th over 64. All right, from here, let me take over for a bit. I'm going to get everything on one side. Actually, I'll do one more thing here. Let's not deal with the fractions if we don't have to. So I'm going to multiply both sides by 64. And I have x to the 4th minus 64x equals 0. All right, now what?
Well, this just looks like the difference of squares.
Not quite, because I got, if it was x to the 4th minus 64, then I would believe you, but that other x causes a problem. There is another way I can factor this.
Couldn't you? Well, first get rid of that x. You could just factor it out and then divide it. So
So now that I have these two factors being equal to 0, then that gives me x equals 0 and x equals 4. So now I know that basically my integral is going to look something like this. Or I don't want to start writing it because I still need a little room. I'm going to be integrating something over the interval 0 to 4. But I can't remember who asked this question, is how do we know which is the upper function and which is the lower function? So that is absolutely something we should figure out. So how can we determine now which function is upper, which function is lower?
Plug in a value in between and check which is like giving a greater output or something.
Sounds great. So we know between 0 and 4, so pick your favorite number in between 0 and 4.
2.
2 sounds good. So if x equals 2, then we have 2 times the square root of 2, and we have 2 squared over 4. Which one of those is bigger? Pretty sure it's the left. Because this one's just equal to 1. So that right there, I think that was the missing piece here. That should tell us everything we need to know about how to set up this integral to find that area. So like I said before, we know we're integrating from 0 to 4. And we know that we can get away with just doing one integral. So what's that one integral going to look like?
Two square root x minus x squared over 4
Yep.
and dx.
All right, very good. So now let's take this integral. I'm going to do a little bit of a rewrite here. 2x to the 1/2 minus 1/4 x squared. All right, back on you. Walk me through this integral, somebody.
So you would take the integral at x equal to 4. So 4 to the 1/2 minus 1 over 4.
So be careful there. It looks like, it seems like you're already trying to plug in these limits. We have to integrate first.
So take the antiderivative first.
Yep, we need to do.
So that would be 3 over 2, like 4x over 3, x to the 3 over 2.
Okay. I'll do this for now.
Minus, yeah.
Yeah, the fractions are maybe a little much to deal with all in one shot. Right, from here we get 4/3 x to the 3/2 minus 1/12 x cubed. And now you're just evaluating it at the limits 4 and 0. So I should get 4/3 times 8 minus 1/12 times 64. And then plugging in 0 is going to make everything else vanish. So that should be 32 over 3 minus 64 over 12. And I believe 16/3 is what we're looking for. One question I want to ask, since we, this was a consideration we had to spend some time on. What if we were wrong about what the upper function was? What if we concluded that what if the integral we took was x squared over 4 minus 2 radical x? What would that have done to our answer?
It would just be a negative value, right? Or something. I don't know.
Yeah. I mean, so let's say you made that mistake, but then you carried everything correctly, then we would have gotten negative 16/3. But that should be a giveaway that you need to go back and look at something. If you do these correctly and set it up correctly, the area should be positive. Any questions on this one before we go on? I'm going to go ahead and skip that one. And this one's a good one to look at. So I want to find the area of the region bounded by y equals sine of x, y equals cosine x, x equals 0, x equals pi. So one thing to be, let's talk about our last example we did. I did not give you the interval we were going to integrate on. We had to find it. And we ended up finding x equals 0 and x equals 4. So that tells us a couple of things. One is more obvious. That tells us where those functions are equal. Those functions intersect at x equals 0 and x equals 4. The other more subtle thing it tells us that might even be more valuable is that those functions intersect nowhere else. So in solving that equation, we found that they cross at x equals 0, x equals 4. We found that they only cross there, which is actually really valuable. So, and the reason I bring that up is for this example, we have x equals 0, x equals pi. That's the interval that I'm interested in. But I don't know if y equals sine of x and y equals cosine of x. I don't know if those intersect anywhere else in here. Because if they do, we're gonna have to do something a little different. So maybe we can start by sketching out. I'll do this above so I don't run out of room. So we're now going from 0 to pi. Pi over 2, pi, -1, pi. So sine of x, I know sine of x goes something like this. So it's going to be a half a period. So it's going to come back down to 0 at pi. Cosine x is going to do something a little different. It's going to start, why did I put a pi there? 1. So here's the thing we have to worry about. There is a crossing point on this interval. So how many different areas are we going to have to find the area? Basically, the area I'm looking for is this. So in the last couple of examples, we were able to get by with a single integral. Are we going to be able to get by with a single integral this time?
No.
No, it's going to take 2. So let's do this. We're going to divide this up. We'll call this area 1, and we'll call this area 2. So let's find area 1 first. How would I find that area? What do I have to do?
Find that intersection point.
Okay, so that's one of the first things we need to do. So I'm going to erase this because, yeah, that's really crucial because that's going to be needed for both area 1 and area 2. How do I find the intersection point? If I want to find the intersection point between any 2 functions, what should I do?
Set them equal to each other.
Yep. So let's do that. So I got sine of x equals cosine of x. Few different ways to figure that out, but I'll do this. Let's divide both sides by cosine x. And that gives me, what's sine over cosine?
Tangent.
Tangent of x equals 1. And what is that angle where the tangent of x is equal to 1?
Pi over 4.
Pi over 4 in stereo. So now we have, I think that was maybe the last thing we needed to find area 1. So now we should be able to set up the integral. And really, this is what we just found. We're going to integrate from 0 to pi over 4. So what is our integrand?
Cosine x minus sine x.
Right. So our upper function is cosine of x. Lower function is sine of x. And back to a question that was asked a while ago. I mean, we have terms that are added or subtracted. That means we can handle them one at a time. I don't need that. What is the integral of cosine of x?
Sine of x.
Sine of x. And the integral of negative sine of x.
Cosine of x.
Positive cosine of x. Now it's just a matter of evaluating here. So I get sine of pi over 4 plus cosine of pi over 4 minus sine of 0 minus cosine of 0.
Sorry, this might be a stupid question. How did we determine that it was cosine of x minus sine of x and not the other way around?
Not a stupid question at all. I mean, that's one of the most important things to do here. Bottom line is, and this is going to be the answer for no matter what the functions are, is it's all about which function. So over the interval 0 to pi over 4, which function is greater? And we know that since the cosine function intercepts the y-axis at 1, sine function goes to the origin. So the cosine function is going to be greater.
Okay, thank you.
I'm making the assumption that you all can see this red dot cursor. Is that true?
Yeah, I just wanted to be 100% clear
Okay.
about that.
Okay. Can you all see my cursor wiggling around right now?
No.
No.
Okay, excellent. Okay, then I'll stop doing it. But yeah, this area right here, yeah, the cosine function is on top, and you'll see that as we go into area 2, we're going to use the exact opposite setup. I know that sine of pi over 4 and cosine of pi over 4 are equal. That's how I found that angle. What is the sine of pi over 4?
Root 2 over 2.
2 over 2 plus root 2 over 2. Sine of 0 is 0. Cosine of 0 is 1. So this area right here is going to be radical 2 minus 1. So we're not done, but that's an important piece of data to have. All right, now I want to find area 2. What interval am I integrating there?
Pi over 4 to pi.
Pi over 4 to pi. And now, what is the function we are we're integrating this time?
Sine x minus cosine x.
Sine x minus cosine x for the same reason. Over this interval, the sine function is greater. And somebody explain to me why I can just make this shortcut. Why do I know this is going to be the integral? Negative sine x minus cosine x.
Well, based on your previous explanation in the graph, oh, you're asking why we are making it negative sum. Sorry, I misunderstood the question.
Yeah. So first of all, are you convinced that the integral is just negative sine x minus cosine x? And really the only shortcut I'm taking there is that I know that basically my integrand for area 2 is exactly the opposite as it was for area 1, which means that the integrals are going to be exactly the opposite. So now from there, I can just start evaluating negative sine of pi minus cosine of pi plus sine of pi over 4 plus cosine of pi over 4. Sine of pi is 0. Cosine of pi is 1, so no, it's not. Cosine of pi is -1, so this becomes +1. Plus radical 2 over 2 plus radical 2 over 2. So now I get 1 plus radical 2. So now from there, I'm able to finish this up and find both areas, or find the full area. I should get 2 radical 2. All right, so a lot of different things here. So a couple checkpoints to look at here. Do we understand why this needed to be divided into 2 different intervals? Do we understand how we made that decision? Do we understand why this integrand is cosine minus sine and this one's sine minus cosine? So I'm not necessarily asking for anybody to answer those questions in particular right now, but those are the kind of things to think about. Those are all kind of the moving parts of this question here. Or anything else I haven't thought of? Anything else you want to ask me before we move on? Okay, let's see what else I had for today. Yeah, let's do this one and we'll end here. So I want to find this area here. Oh, go back. And I wanted to do at least one example here, and I'm kind of I'm definitely missing my first goal, which is to be done by 8:40, but I'll have to recalibrate. Want to find this shaded area here. Now, most of the time when we do integrals, we are dealing with what as our independent variable? X or Y?
X.
Usually dealing with X, right? And that's just what we're used to. Sometimes it doesn't make a whole lot of sense. For example, in this case, if we were going to use X as our independent variable, you know, we'd have rectangles that look like this. But then, you know, the top and bottom of this rectangle are both going to be governed by the same function. Over here, the top of that rectangle is going to be given by the pink function, and the bottom is going to be given by the blue. Basically, you're going to have to be doing multiple integrals. So this is one of those situations where it makes sense to deal with this in terms of rectangles that look like this. So these are long, narrow rectangles that have I'm using Y as the independent variable. And basically, no matter where I draw this rectangle, which function is going to give me the left end of these rectangles? So I'm not hearing it. Hopefully you're all thinking it, or many of you are thinking it. But the left hand of these the left side of these rectangles is all going to be given to me by this blue function. The right hand side of these rectangles is all going to be given by this pink function. So typically the way we've looked at these is like this. We have an x min, an x max. Basically, that's your interval where you're trying to find these areas. And you have an upper function minus a lower function. And you integrate those with respect to x. We're not going to be able to do the exact same thing this time because we want to use y as our independent variable. So we're going to have to translate to make that work. So now instead of some maximum x value and some minimum x value, I'm going to have a maximum y value and a minimum y value. And let's say these are all, dy intervals here. Within a given dy interval, basically, when I'm inside one of these rectangles, I am having y be a constant, and I'm letting x be the variable. So since x is being the variable, it doesn't really make sense to talk about upper versus lower because they're all on the same level. They're all on the same vertical level. So instead of looking at upper versus lower, and really let's talk about this. Why do we do upper versus lower? Really, we're doing greater minus lesser. So when we're looking at y values, greater means above, right? And lesser means below. So if we translate this to kind of the x arena, I want the function on the right to come first and subtract the function on the left. Basically, it's all about where are the values greater. And when you're looking in the x direction, the greater values are on the right. The lesser values are on the left. When you're looking in the y direction, the greater values are above. The lesser values are below. So let's go a little deeper here. So let's fill in now. What are my minimum y value and my maximum y value going to be to find this area here?
Zero and 3.
0 and 3. So they gave us the intersection points. We're going to integrate with y as low as 0 and y as high as 3. What is our rightmost function in this case?
Y squared minus 4y.
I think y squared minus 4y is actually.
Oh, yes, the right one.
Yeah.
Sorry, the 2y minus y squared.
Right, but I grant that this is a little bit hard to read. So 2y minus y squared, and that means y squared minus 4y. So I think I'll pause there. I think, computing these integrals is much simpler than setting them up. Any questions about how this integral came to be? Okay. If there are no questions, I'll just simplify a bit before we integrate. So this will be minus 2y squared plus 2y dy, which is going to be minus 2/3 y cubed plus y squared. And I'm going kind of quickly because I think just check me because I'm going a little quickly here. Minus 2/3 times 27 plus 9. Got a little bit of problem. Why did I get a negative number?
Oh, is it,
Oh,
yeah, is it negative 2y squared or is it?
I think the problem's here. 2y minus negative 4y. Well, let's check everything. I believe that, yeah, if we collect like terms here, we have minus y squared minus y squared. So
I
that's
mean,
minus,
Professor, like, aren't almost all the x values like, on the negative side?
yeah, but remember we're integrating with respect to y this time.
Okay, yeah, got it.
Yeah, the area, most of this area is on the negative side. Okay, that makes more sense. I believe the area is going to be 9. But that question that was just asked brings up a good point. So yes, most of the area is to the left of the y-axis, which you would think of as being negative, right? So why do I end up getting a positive? So let me explain it like this. Remember, we are finding the area between curves. So the fact that all this area right here is to the left of the y-axis is not important. What is important is that, I'm finding the area left of the pink curve and right of the blue curve. Basically, I'm looking at the differences between those two functions. And that difference is going to be positive because the pink curve here is to the right of the blue curve. So basically, the length of all these rectangles, those are going to be measured as positive. Let me contrast that with something here. Let me go ahead and erase some of my marks. If instead I was asking for the area underneath, or sorry, not underneath, the area between this blue curve and the y-axis, that would be negative. Because all of that area would be to the left of the y-axis. Does that make sense, or should I take another try at that?
No, that makes sense. Like, but if you could go over it one more time, just.
Yeah. So let me do this instead. So let me actually shade in some of the things I'm talking about here. So let's say I like, it's hard to do, but pretend that pink curve isn't there. I just want to find this area here. Actually, you know what? I got a better idea because this actually came up in one of our other examples, which we did in the x-axis. Oh, here it is. So here, let's just focus on area 2 here. A lot of this area for area 2 is actually below the x-axis. The reason that doesn't really matter, the reason it all ends up being positive is because I'm looking at the difference between this upper curve here and this lower curve here. But let's say I was looking at this. Let's say I just wanted to find the area between. Let's just say I wanted to find this area here, this darkened area. So basically that would be this. That would be the integral from pi over 2 to pi of what function is this? Cosine x dx. If I were to find that area, then basically what I'm doing, I'm finding the area between cosine x and the x-axis. And since all that area is below the x-axis, that's going to give me a negative number. So instead, let's try to think of this as the area between two curves, where one of the curves is cosine x and the other curve is the y-axis. Now, to find that area, we have to think about which curve is on top. So which is the greater curve, the y-axis or cosine x? Sorry, the x-axis or cosine x?
The x-axis.
The x-axis, right? So that means when I set up this integral, it's going to be 0 minus cosine x dx. So this one right here is going to give me something negative, but this one right here would give me something positive. So hopefully that's a little more clear. If you want to talk about that a little more at the start of tomorrow's class, we definitely can, but I've already kept you later than I bargained on. So if someone could go to Canvas and confirm for me that the quiz